Hello, I'm Alexey Fedorenko from Skolkovo Institute of Science and Technology, which is located in Moscow. Thank you for your interest to this topic and to my presentation. It is about high rate damage modeling in composite material. Here is the content of my presentation. First, I start with a brief introduction to examples of composite structures which serve as energy absorbing components in different industrial applications. Then, since modeling of crush process is in the focus of this work, so a damage model for the case of quasi-static loading will be proposed at first, and then it will be extended to the case of strain rate sensitivity. Then a numerical simulation examples of composite cube crushing will be provided. After that, short section of results, discussion, and conclusion. First example is a crash tube in the safety system of the seat in a helicopter or airplane, which is aimed during crashing to absorb energy and to reduce overload to person on the seat. Another example is a special structural element between cargo crossbeam and lower frame of the airplane with the same goal to reduce overload in case of emergency landing. Here is a Formula 3 composite noise. This is the entire structure which absorb energy during collision and also reduces overload to file. To characterize dynamical properties of the material, a special test should be conducted. Here is an example of tubular specimens which frequently used for material rate characterization. Here is a typical experimental setup for strain rate characterization of composite material. It's based on tubular specimen subjected to impact of a falling mass or fixed to that falling mass. Specimen has chamfered end, what is important for correct failure initiation. The general characteristics obtained from this test are specific energy absorption with the meaning of force average over crushing distance, and another characteristic is specific crushing stress. Typical load displacement diagram is presented on the right, so you can estimate importance of end chamfer of the specimen. In case of flat square end without chamfer, the response of specimen is very stiff, and failure may occur far from the contact with mass, so the crushing process is not appropriate. Main parameters which we can vary is impact velocities, layup, and chamfer geometry. Failure mechanism is difficult to characterize, as you can see on these pictures, but some key patterns can be detected, such as possibility of cracks, fiber deployment, or crash to debris of small pieces. Tubular specimen may be considered a structural element. So on the lower level of coupons, a very popular impact experiment is based on split Hopkinson pressure bar. It records reflected and transmitted strain waves, so strain in the piece of specimen can be determined. As you can see on the example of test results, transverse and shear loading diagrams are highly nonlinear and rate dependent. They have a significant hardening with rate growth. In fiber direction, hardening effect is not so meaningful, but ultimate strength grows with impact rate exists. Also, from literature sources, we can conclude that tension properties are not so sensitive to strain rates, so they can be omitted in the analysis. This work proposes a model of composite material damage and failure. It's based on continuum damage mechanics concept. We introduced two damage parameters. Psi1 is associated with fiber failure and Psi2 with matrix failure mode. Damage parameters can be considered as multipliers to elastic constants, and it can be interpreted as a degree of material stiffness reduction during damage accumulation. Maximum failure stress initiation criterion is chosen for simplicity, and on these diagrams you can see assumptions for damage constitutive law. For longitudinal load, we reach ultimate stress at point 1 in case of load increase. Then the load suddenly drops to up to zero value, which corresponds to failure strain. But in case of unloading at point 2, we reach back to the point 3. Slightly another assumption for transversal load and shear load. So at first we get some stress value at point 1 where damage growth initiates, and then we have nonlinear part of load, and with reaching to some constant value, and in case of unload we go back to the 0 point. To realize this idea, a damage evolution load based on strength dependency from damage parameters are presented, and constants can be easily determined based on strain and stress limit values. In order to capture strain rate sensitivity, now we make the following assumptions. Now, strength characteristics are the functions not only damage parameters but also their rates. A second assumption, as mentioned previously, we assume that tension characteristics are not rate dependent. And the third assumption, that we can decompose stress function to static and dynamic parts as presented here. In case of quasi-static load, the dynamic multiplier should be equal to unity. And here you can find a complete set of relations which are inspired by Johnson-Cook hardening equation, with the modification that here damage parameter has a similar role with equivalent plastic strain in Johnson-Cook model. Next problem is parameter identification, and it can be resolved using stress strain diagrams for a set of strain arrays. For a particular strain array, we can write the following equation. which can be transformed to ordinary differential equation with initial condition of undamaged material, and then we do initial guess of the parameter, solve differential equation, and compare with the test curve. If the fit is not satisfying, we vary parameters. Um, so a special procedure is developed in case of we need to improve the fit. On this slide, you can see the procedure of parameter identification for other two stress components in second and shear stress components, and identified parameters based on solved differential equations. Now we consider problem of numerical simulation of impact to typical tubular specimen on the basis of developed material model. It was accomplished by Abacus explicit software with implemented subroutine. Here is elastic properties for the selected problems, the dimensions of composite tube, and the chamfer zone is selected to 30 degrees. We use 0 degrees orientation in axial direction and 19 degrees in hook direction, as shown in the figure. So the ratio between axial and hoop fibers is 1:3. This is a simulation of crash process. Fiber failure is chosen as element deletion flag. So damage. So for elements damaged in other modes are stay on the picture, and you can observe accumulation of material debris. On the slide you can find load versus displacement diagram during crash process. At the initial stage you can see a sudden drop of the reaction force caused by chamfer failure, and then stable crash process begins, and we calculate specific energy absorption characteristic for the first 5 millimeters of the stable crash path and for the second. So if we compare, we can find that on the first pass it is significantly higher than on the second pass. Straightforward conclusion is that strain rate dependency should be considered in impact problems. I would like to emphasize that there are some particular materials, particular problems where there are no strain rate dependency, but anyway it should be verified. Proposed model is able to capture strength and handling dependency on different range and types of loading, and numerical simulation of composite tube impact test was demonstrated. An important result that crashworthiness varies along tube length, so crashworthiness averaged over tube length may lead to underestimation of reaction force in engineering applications. Thank you for your attention, and I will be happy for your response.